In this video, I'm going to talk about the axial point groups, which are point groups containing a single unique principal axis that has the highest order rotational symmetry to it. And what I have written here is essentially what I'm going to be talking about throughout this video using pictures and things like that. So you can read through this in the lecture notes linked to in the description down below, but I'm just going to continue on to getting to these pictures here. And so our first sort of group here that we have is the pure enfold rotations. And so that is 360 degrees divided by n degree rotations, or if you prefer radians, it's 2 pi over n radians. And so this is the CN group. And so the first one, C1, is just the identity element. There's nothing you can do to it except the identity element. And that'd be something like this right here, which is the bromochlorofluoromethane. And so that has a bromine, it has a chlorine, and it has a fluorine, and then a hydrogen attached to a carbon here. And so this is a chiral molecule, and you can't rotate it or reflect it or anything like that in any way so that you could get the same thing by through a rotation of some degrees or anything like that. So all there is the identity element. Then C2 is one that has only a 180 degree rotation that it can actually go through. And so that would be something like hydrazine in this gouge conformation right here. So that has C2. And it's kind of hard to see what the C2 symmetry is here. And so I actually have this different thing right here. So this is 1,3-dichloroalene. And so it kind of shows where that C2 axis is right there. And so you see you have to kind of stagger it up like that, which is kind of a symmetry that is a little bit harder to find, I think, especially when using these two-dimensional images. And so that is the C2 symmetry. C3 then has the C3 and then the sort of opposite C3. And an example of that would be triphenylphosphine, which is what we have right here. And so that has a phosphorus here in the center, and then it has these phenyl groups on it. And so you can do a rotation 120 degrees, but there wouldn't be any sort of reflection you could do because these phenyl groups are sort of tilted at a weird angle, so that they're more like fan blades or something. And so there are no reflections, there's no other rotational axis, and so that is a C3. Then of course the C4, C5, C6, just add those other ones on there. And the thing to notice here too is I have C4, then C2, then this C4 bar. That's because C4 twice is just the same as a C2. A C4 is a 90 degree rotation, so 290 degrees is a 180 degree, and that is just a C2. And so we see kind of the same thing here for C6, that we have the C6 and a C3, which is just two C6s, then a C2, which is just three C6s. And we have the C3 bar, which you could think of as sort of four C6s or two C6s in the other direction. Then this C6, which you could think of as five C6s or one C6 in the other direction. And so C5 rotations, so I just put this pentagon here, and so you could see how C5 you can sort of rotate around this 5 times. This doesn't work well because this actually has more symmetries than that, but I just wanted to show how sort of a 5-point rotation would go. And so that is the CN groups. And so everything after this is sort of taking the CN group and then adding another generator to it, and then using that to generate more elements of the group. And so our CNV, we now have this sigma V on here. And so this table works out kind of nice because you can see sort of on this side, this is just the CN groups here, and then we sort of added these sigmas onto it here as the new generator onto this side right here. And so this just takes the CN groups and then adds this sigma V generator here. And I guess one other thing to point out now that we're sort of getting a little bit further is I have some of these things boxed off in each row, where each row is a particular group, and I have some of these things boxed off, and the boxing off is boxing them into classes. And so if you've seen my earlier video about classes, then that is what that is. So for C4V, for instance, the identity element is a class. We have this C2 here, that's a class. Then these two C4s here that are a class, where the C2 is actually two C4s taken one after the other. And then we have our sigma V's here and our sigma D's, which are both in their own classes. And so looking at some molecules that are examples of this, so water is, H2O is a good example of C2V. So we have our C2 rotation axis, which is 180 degrees, and then we have our two reflections. So we can reflect across there, or we could reflect across there. And so that is our two sigma reflections there. Ammonia is C3V, and so we see this has three rotations of 120 degrees. We now have these three sigmas here because we can reflect across there, or across there. Then we have this bromine pentafluoride, which is C4V, where you see we can rotate this around 4 times, so 90 degrees each time. And so that is so 2 rotations in a row would be your C2. Then we have sort of the C4, then the C4 bar going that way. Then we have our sigma V1 and our sigma V2, which would kind of be planes across here. And so we can think of this as sort of 1, 2, 3, 4 here. And so these sigma D's, 2, 3, and 1, 2. So 1, 2 would be sort of splitting between the 1 and 2, and then the 3, then the 2, 3 would be splitting sort of along this way. And so we have all those sort of planes of symmetry there. And then C5V would be more, and then C6V would be even more than that. So we have these rotations on this side, and then these reflections on this side. Then so we get to sigma H symmetry, which now adds, well, we don't necessarily have the sigma V's from the CNV above up here. So we don't have these sigma V's. We're just taking the CN and adding the sigma H here, which is a sort of reflection on the plane of the screen. And so if we have some object like this, some diamond-shaped object, then when you reflect into the screen, it would take some element here pointing out of the screen and sort of reflect it down to the bottom of it beneath the screen. And so we see here, once again, on this side, we have our CN groups here. And then what we're doing is we now take this sigma H and we sort of act the sigma H on the C2. That gives us this S2, which is the same as an inversion, so we could use that as I. We take these two C3s here. If we do a sigma H on either one of those, we get this S3 or this S3 bar, and so on and so forth. And so that's kind of how to read this table, is the S's on this side are sort of taking our rotations from this side and then acting on it with the sigma H. And so we can look at a few example molecules of that. So this one bromo, one chloro, two fluoroethene right here. So we see that that is C1H because all it has is the identity element, or the sigma H, because there is no way to sort of rotate it around to get it to sort of overlap with itself. But you could reflect this in the sort of plane of the screen so that this F and this bromine and this chlorine, so the fluorine, bromine, and chlorine just kind of reflect into the screen, but stay where they are position-wise. So then the C2H, we can use this difluorodiazine here, and so that is this. So we can see that we could rotate this around 180 degrees, which is why it's the C2, but we could also do an inversion of it, and so that would be sort of twisting it around this way so that this F is sort of now down on this side here, and this F is sort of twisted up to this side here, and then we actually do a reflection sort of across this plane right here so that this F ends up over there and that one ends up over there. And then of course we have the C3H, which is boric acid. So you can see how this has the C3 symmetry because we could rotate these around this way. So the 120 degrees around that way each time. So you can see how if we did like a single C3 and then we reflected it in the plane of this, we would still end up with the same thing, and those are our S3s here, because we just take this oxygen right here and sort of move it down to that oxygen and then reflect in the plane of the screen, and so that would just give us the same thing again. Then C4H, we have the C4s and then these S4, S2, which is just, sort of like a double S4, then the S4 bar, and so on and so forth through all of these. So that is the C and H group. The S2N, so this S generator can act as its own group generator. So something like this 1,2 dichloro, 1,2 difluoro, that should actually be a difluoroethane there. Looks like this. So we see how if we sort of took this and sort of wrapped it around that way and then did a sigma reflection in the screen. So we are sort of rotating it around an axis that's pointing sort of in and out of the screen right here, so that this chlorine ends up where this fluorine is, and then we reflect it on the plane of the screen, then that chlorine would end up right here. There's no other symmetries on this, so like I said, this should be difluoroethane, fluoro, and so that is an S2 group. I was hard pressed to find anything that was an S4 or an S6 group. This is an S6 operation here, but this molecule would actually have other symmetry that it would satisfy, and so it's not actually an S6 group. But I talked about how the S6 happens in the previous video, how essentially it's sort of rotating 60 degrees down that way, so our HA is here, then reflecting so that this solid bar 1 ends up as a dotted bar pointing back, the dotted bar pointing back ends up as a solid bar pointing forward. But anyway, we'll move on to the DN group, and so this is the CN group, and now we are adding another C2 as a generator here. And so we see once again on this side right here we have our CN groups, and then we are adding this C2 generator here, so C2. And so this one right here is sort of like taking our new generator and acting it on E here. And so that just gives us the same thing, so the C21. But if we act it on the C2 principal axis, then we get this C2 1, 2 here. So we can kind of do the same thing. So with the D3 here, so we have the C2, 1. If we act it on the identity element, that gives us the C2, 1 here. If we act it on this C3, that gives us this C2, 3. And if we act it on this C bar 3 here, that gives us the C2, 3 right here. And so an example of this one would be ruthenium triethylene diamine, which you can see right here. So this is what the molecule looks like, and it doesn't work that well on here because this is a static image, but in the lecture notes you can actually click on this link and go see it, and you can actually play around moving this around to actually get a good look at these rotation axes here. But we can look at it in 2 dimensions right here. So if we're looking sort of down onto the ruthenium here, we have this C3 axis where this nitrogen moves over to there and this nitrogen moves over to there. But then we also have these C2 axes right here, which would be these 3 C2 axes right here. And so that is our ruthenium triethylene diamine. Then we could do the same thing. So we have our E and then our C4, C2, C4. We act our new generator on the E. It gives us the thing back. We acted on the C4. It gives us this. We acted on the C2. It gives us this. Acted on the C4 bar, and it gives us this. And you can continue on that way for each of the elements in this group. So then we can actually add the sigma D symmetry. So now we have our CN group plus the symmetry operation from the DN up here. And so CN plus this was our DN. And so we essentially have the generators of our DN group here. And then we are adding this extra sigma D generator here. And so once again we are so this is kind of split into 2 rows here. So we see we take our new generator, acted on E, that just gives us our new generator back. We acted on the C2 principal, and that gives us this new sigma D, so it has the 2, 3 up there rather than the 1, 2. We acted on one of our C2 axes from the DN group, and that gives us an S4. We acted on the other one that gives us this S4 bar. And so you can see how we just take the group from before essentially and just add this new generator and acted on each of those. And so you could do the same thing for D3D, which is just taking the D3 from above in this first row up here and then acting that sigma D1, 2 on each of the elements. And so each column is sort of, how the element from the previous group and then the new generator acting on that element from the previous group. And so allene is an example of the D2D here, which has obviously the E, the C2, these other 2 C2s, and then it has these S4s, which you can actually see how that works right here. And once again, you can click on the link here and actually play around with this in 3 dimensions. And so this I just put here again because one of those C2s is kind of a difficult one to find because of the way that these things are sort of staggered. These hydrogen atoms are staggered from each other. And so that is one of the C2s right there. The other ones, well, we have this C4 here. And so that C4 is actually giving us the C2 here. So when you the C4 is just for the S4 operation here because the C4 isn't actually a symmetry element of alene because you would need to go the full 180 degrees if you wanted to get back to where it was or you want it to overlap with itself. And so that is the other C2 operation right there. And so that is the DND, which you can see is somewhat truncated here, and that's because the higher order DND groups can actually be reduced down to other groups, and so you often see this as a sort of truncated table. Then we have our DNH, which is we are taking our DN group here, so not the DND, but the DN group, and then adding this sigma H generator to it. And so this, once again, can be read the same way, where this sort of top row for each group is the DN group, and then this one is when you act sigma H on it. So you act sigma H on the identity, and you get sigma H. You act it on C2, you get this inversion here. You acted on this C2, you get this sigma V. You acted on this C2, you get this sigma D, and so on and so forth for each of these. And so that's how you can read this table here. And so here are some molecule models here that we can look at for these symmetries. And so the thing to notice is, so we have the C2 here, which is this square planar, but it has a different, or it has this molecule here and here, 180 degrees from each other, but then these different ones on the other axis here. Then the C3 here is the D3H, but the thing to notice here too is that we have this D3H, this D3H, and this D3H, and so all three of those satisfy D3H. But this one right here is the boron trifluoride, which is the pretty common example for this one, which looks like this. So we have these three reflection planes. We have these three C2 axes here, and then our principal C3 axis right there. And so those are the rotation and reflection axes for the D3H there. And of course we have these S3s as well, which are essentially just you rotate it this way and then sort of reflect it into the page, which gives you that S3 that S3 operation there. Then we have these D4Hs, and I guess the thing to notice for both these and these additional D3Hs is that we have these molecules sticking, or atoms rather, sticking off on the top or bottom, and those atoms that stick off the top or bottom both have to be the same in order for this to have the D3H symmetry. And it's the same for the D4H. These have to be the same here, or we can have this square planar molecule right here. Then the DH5 just has the 5 around the equator here, and then these two on the poles right here, or this sort of pentagonal planar here. And then of course benzene is D6H, and I went through this in the previous video, but we see we have the C6 axis right here, but that can also act as an S6 axis. We have the sigma H, which is just reflecting through there. We also have this I, which is, so that would be this I up here, which is an inversion. So you're essentially just trading places between each of these sort of cross carbons like that. And so that's what an inversion is. Then we have all these additional C2 axes here. We have these sigma V reflection planes, sigma D reflection planes. And so that's what you can see as the elements for the D6H up here. And so for the D5H, I put the ferrocene eclipsed right here. And so that works as a D5H. Because we have this five-fold axis sort of around this way. But then we have, if you kind of go through the iron at each of these corners, we have these C2 axes here. And you can see how this can be reflected in a plane like this, so that sigma H would reflect this down to there and this one up to there. And so that is the D5H there. And we would have these S5s and so forth as well. But anyway, those are the axial point groups. So I guess the kind of a broad take-home message here is just that we sort of start with this CN group, and then in each subsequent group we are just sort of adding a different additional generator to each of them. So the SN, I guess you can kind of think as being like a CN sigma, a sigma H group. And so using this as like its own sort of unitary kind of generator thing. And so that's how you kind of add this to the CN, even though that's what we have up here, but this is kind of treating it a little bit differently. And so, yeah, we're just adding these additional generators onto here, onto each one of these. But anyway, I hope you found this video helpful, and I will see you in the next one.